Great. Thank you, Tony, indeed. It's certainly true that I haven't been here before. That's my mistake. It's kind of a beautiful place. Sorry about that. Do we need this light? Oh, that's the projector. Of course we do. Now, I didn't expect quite so many people, and indeed, the talk that I'm going to give is, I'm probably, as Tony said to me, preaching to the choir, but it's not going to stop me from preaching. But let me waste a few minutes at the beginning by continuing Tony's discussion of things that happened long, long ago, and I have a number of little incidents of travel on the way to here that I would discuss with you. So the first one has to do with my thesis exam, which took place in Madison, Wisconsin, because my thesis advisor, Schwinger, had left Harvard for the summer and was in Madison. And so we had this committee consisting of Schwinger and a bunch of other people, and Frank Yang. So this has to do with Frank Yang. He was on the committee. I started talking about my thesis, which had to do with the unification of weak and electromagnetic forces, but I hadn't really accomplished very much at that time, even though Harvard was willing to get rid of me. We'll come to that in a moment. But so I was explaining why there were two neutrinos, electron neutrino and the muon neutrino, and they were different from one another. Now this is 1958, and Schwinger had taught me that there were two kinds of neutrinos. And then Yang pops up and he says, Mr. Glashow, that statement has no meaning, no experimental consequence for electron neutrinos and muon neutrinos to be different from one another. And I said, well, I'm sorry, I didn't know what to say. And Schwinger got up and explained to Yang that you make beams of one kind of neutrino and you produce electrons, that there was a conceivable experiment you could do. And then Yang shut up and I talked a little bit more and got my degree. But wait, that's 2 years later, Li and Yang write a paper suggesting that it might be a good idea to do an experiment to tell the difference between muon neutrinos and electron neutrinos, giving no credit to Schwinger. That's my Yang story. I checked it out with Yang just 10 years ago, and I explained to him what happened from my point of view, and he said, yes, Shelley, that's exactly right. That's what I did. The next story has to do with the Soviet Union and Copenhagen. You see, I got my degree for not creating an electroweak theory, and it didn't work. I was going to go to Russia. For some reason, I convinced myself that a year in the Soviet Union at the Steklov Institute would be a sensible thing to do. And I was prepared to go there, but I didn't have my Russian visa, my Soviet visa, so I went to Copenhagen instead. And I befriended the Soviet consul in Copenhagen, invited him to parties. He would bring vodka, and a very nice person. I would say, is my visa ready? He would say, visa not ready, soon, soon. And a year and a half later, I gave up on him, went to Bern in Switzerland and asked about my visa, and they said, visa not coming ever. So I ended up spending 2 years in Copenhagen and CERN. And that was good for me because I ended up writing that paper that was the earned me a portion of the Nobel Prize. So that was another story. Next story. We come to 1961. While I was in Copenhagen, I was invited by Murray Gell-Mann to come to Paris because he liked my paper, I guess, and I talked to him and explained what I had done. And he liked it very much, so he invited me to come to Caltech as a postdoc. So the next year I came to Caltech, where I met Sidney Coleman, we wrote a lot of interesting papers. I might skip along, because something very exciting happened. Murray Gell-Mann came out with the Eightfold Way, and that became a fascination of mine and Sidney's for a few years. But that paper on the Eightfold Way, which eventually, as some of you might know, became a Caltech synchrotron laboratory report and is often referred to. The Eightfold Way, which is flavor SU3, that paper, the original version, was co-authored with Richard Feynman. Feynman and Gell-Mann had collaborated, learning group theory quickly. But physicists didn't know what SU3 was, so they talked to mathematicians, and the paper had both names. And Feynman, however, decided that it was too crazy an idea. He didn't want to be associated with it. He removed his name from the paper. And nobody knows that, except nobody living knows that except me. So you can't check me on that. That was 61. I'm going to move through a few more years. The next year I want to talk about is 1964. And last year was the 50th anniversary of 1964. And what a year that was. I would like to remind some of you of the 7 things that happened in that year, each of which was enormously important. The CBR, cosmic background radiation, was discovered in their paper, Penzias and Wilson, was published in 65, but the experiment was done in 64. The observations were made in 64. Fitch and Cronin, Fitch just passed away just last week, Fitch and Cronin discovered CP violation in 1964. Nick Samios discovered the omega minus particle, which completed the decimet of fermions with spin 3/2 in 1964. And it was that made everyone believe in the Gell-Mann-Neyman flavor symmetry. Before that, I was making lots of money making bets with people about the validity of flavor SU3, and with Samios's discovery, I could collect those bets. Also in 1964, Oscar Greenberg introduced the notion of parastatistics of the quarks, which, by the way, were also introduced in 1964. In February of 1964, Gell-Mann introduced quarks, and a little bit later the same year, Greenberg introduced quark color. Peter Higgs, who I had just met the year before at a remarkable summer school in Newbattle Abbey, which is an ancient rat-infested place in which we had a wonderful time drinking Hungarian wine provided by Higgs. We were having lots of conversations about the possibility of unification of weak and electromagnetic interactions and gauge theories and all that stuff. And Higgs was not listening to it. He was busy with the distribution of wine to the members of to the visitors. Had he listened to us and then did what he did in 1964, things might have turned out rather differently. Anyway, it was 1964, the Higgs mechanism. Higgs plus 5 other people introduced the Higgs mechanism. As I said, quarks were introduced in February of 1964, and toward the middle of 1964, Bjorkane and I introduced the 4th quark, the charmed quark. So that was rather a remarkable year. Enough for 1964. Let me turn to 1970 and a story involving Steve Weinberg. You will know that Steve introduced spontaneous symmetry breaking and made sense of electroweak unification back in 1967. Nobody took it very seriously at that time. Certainly nobody took my SU2 cross U1 paper, least of all me, seriously in those days. But then in 1970, nobody took charm very seriously in 1964, until Iliopoulos, Mayani, and me at Harvard got together and realized that this 4th quark could be useful, could do something, cancellation of strangeness, changing neutral currents and all that. So we wrote our paper, the JIM mechanism, and the 3 of us, John Iliopoulos, who sounds Greek but is French, Luciano Maiani, who sounds Italian but is San Marinan, and I, who sound American and am, went off to MIT where Steve was teaching and explained to Steve what we had done about charm about introducing the charm quark into the theory where it would actually do something useful. And he said, more or less, quoting, "Ho hum, didn't sound interested at all, although it was the Jim mechanism that would enable his own theory of leptons to be extended to what is today the electroweak theory." So that was kind of strange. Do I have anything else? Well, 1979 was particular fun, of course, when Steve and I, at that time both at Harvard, discovered that we had won the Nobel Prize together with Abdus Salam. And not only that, Abdus Salam had told Time magazine how proud he was to be the first Muslim to win the Nobel Prize. So we sent him, Steve and I, a telegram. "Dear Abdus, we didn't know that Sadat had converted." Because Sadat was the first Muslim winner of the Nobel Prize. Just whatever. So various interesting incidents. How lucky I was that I never got the Soviet visa, because otherwise I would never have won the Nobel Prize. Let me now talk about a parable of the pure and the applied, and use this wicked machine. Now, I don't want to read all this. I mean, we know many politicians and opinion makers insist that governments and universities should invest only in research that makes money or is immediately useful, and we know that that's senseless. They're wrong. I have a couple quotes like this. Fundamental physicists would be hard-pressed to point to anything useful that was directly dependent on their theorizing. If individuals wish to contemplate the universe, as many of you do, let them do it in their own time, at their own expense. It is far more important that we encourage our best brains to solve real problems and leave theology to the religious professionals. That was from The Economist. And of course, had Faraday, Roentgen, and Hertz focused on solving the real problems, we would have waited a bit longer for things like electric motors, X-rays, and radios. Well, this is more on the same issue. Again, just recently, the American Academy of Arts and Sciences was writing that virtually every new technological product is traceable to a research discovery, often one pursued with no application in mind. We all know that, and so don't even bother reading the rest of this. I wasted a lot of time at the beginning. Today's fundamental, well, I don't know if I speak for everyone here, but they are concerned with exotic phenomena that are not at all useful in themselves. Nonetheless, their work has and continues to make, I think, enormous impacts on our lives. Curiosity-driven searches for fundamental knowledge have always been at least as effective as direct searches for solutions to specific societal problems, whether from the discoveries themselves, or from the technology they lead to, or from the scientists who hone their skills at the frontier of knowledge and then move off in other directions. Quantum mechanics, for example, was invented by dreamers like Bohr and Heisenberg, Schrödinger, Pauli, Dirac. None of those were concerned with applications of quantum mechanics. But today, quantum mechanics, it has been estimated, underlies about at least a third of the world's economy. So dream on. But our critic does have a point, and consider CERN, which has accomplished a number of things. There are lots of people out there, 10,000 visiting scientists from 113 countries. And what has it done? It's found neutral currents of my electroweak theory, of our electroweak theory. It's used neutrinos to confirm the quark hypothesis. It discovered, or Carlo discovered, the W and Z bosons. It counted the number of neutrino species, 3. It created the first anti-atoms, and of course, it found the Higgs boson. And none of this stuff is practical, and I would say totally useless. But Not quite useless, and I have some examples of spin-off. We all know about the World Wide Web, which was developed in 1987 or so at CERN. And fewer of you know that the heating system at Meyran Airport in Geneva is recently been installed, is based on vacuum technology from CERN. And there are many other applications. So, a little digression, since we're supposed to talk about particle physics. I'd like to make the point, as if it's needed, that particle physics is an experimental discipline. And so I mentioned that electrons were proposed by an Irishman in 1891, and they were discovered in 1896 by an Englishman. That photons were proposed in 1905, detected, that is to say, as particles in 1926 with the discovery of observation of Compton scattering. Neutrons proposed in 1920, observed in 1932. Neutrinos proposed wonderfully by Pauli in 1930, discovered in 1956, 26 years later. Pauli was delighted. 1934, mesons were proposed by Yukawa, detected in 48. 1960, W's and Z's were proposed. 1983, they were detected. 1964, quarks were proposed. 1970s, they were sort of detected as best you can as jets. 1970, the 70s, the standard theory, which is a lousy name for which I'm not responsible, emerged. 1980s, it was generally acknowledged to be triumphant. And then there's the Higgs boson, discovered in 2012 at CERN, and a bittersweet year indeed, because it was the last year in which the United States had an operating accelerator at the high energy frontier, and we have no such machine now and probably never will. So it marked the end of an era, also the beginning of a very challenging era. The values of basic research, just a few examples. X-rays were discovered in 1894, CAT scanners, one of the consequences. Antimatter was discovered in 1932. PET scanners use positrons. And nuclear magnetism was discovered in 1950. It led to MRI scanners. So all of the scanning technologies that doctors use evolved from fundamental, rather useless-seeming discoveries. Radioactive isotopes, of course, have many applications today. For example, brachytherapy. Cyclotron has led to particle beam therapy, lasers to all kinds of microsurgeries. The polymerase chain reaction has, among other things, been used in forensic medicine. Penicillin, an accidental discovery. A lot of these discoveries are accidental. I mean, radioactivity was accidental. X-rays was accidental. Penicillin, of course, is very useful, as well as other antibiotics. 1953, well, of course, Watson and Crick, and that's turned out to be rather useful as well. Information technology, same story. Radio waves, discovered by Hertz in 1888, led to wireless transmission soon thereafter, thanks to people like Marconi. 1947, holography, credit cards. 1947, transistors, the first computer revolution. Integrated circuits led to the second computer revolution. Optical fibers, PK, personal key cryptography, secure data transmission, and the application of number theory to finance. This is an interesting evolution. The giant magnetoresistive effect, discovered accidentally by a Frenchman and a German who shared the Nobel Prize, within a few short years led to gigabyte memories on hard disks. Very quick evolution. High-T superconductors don't really have many applications yet. I hope they will. And quantum manipulation, which earned the 2012 Nobel Prize, may someday be relevant to quantum computers. And again, as in the past slide, most of these discoveries led to Nobel Prizes. A few more, you can go on indefinitely, but I love the photovoltaic effect discovered in 1839 that lights can make electricity. And that led to solar panels. The person who discovered the photovoltaic effect was the father of Henri Becquerel, who discovered radioactivity, because his father was a scientist as well. The photoelectric effect, of course, which Einstein explained, led to CCD devices. 1912, X-ray diffraction made possible the discovery of DNA structure. General relativity leads to, or was essential to, the development of GPS systems. Matter waves, de Broglie's matter waves, led rather quickly to the electron microscope. Nuclear fission to nuclear power. I mean, the American enterprise to make a bomb was not intended to lead to nuclear power, but it did. Carbon dating is relevant now to climate research. CCDs, which was on the last slide, CCDs made possible digital cameras. Buckyballs, who knows what they will be useful for. Graphene, well, a lot of talk today. It used to be plastics were the future, now it's graphene is the future. Perhaps that will be true. Again, most of these led to Nobel Prizes. Now this is a big one. Atom smashers, cyclotrons, accelerators are really quite practical devices, and although there are very few of them that are used for particle physics research and forefront basic science, there are some 10,000 operating accelerators in the world today. They're used for most anything by industry and medicine. Skipping to the next paragraph, we know that electrons moving in circles lose a lot of energy due to synchrotron radiation, and that, although once was a problem, is now a multi-billion-dollar enterprise. Synchrotron light has many applications to science and medicine and engineering and industry, and there are about 80 of these devices in many different countries, 20 different countries, large, expensive toys. Of course, the third generation or fourth generation of these devices are called free electron lasers, and this keeps going on and involves lots of money and is very, very practical. Started off as a problem, making it more difficult to make electron accelerators. Now, it often takes a long time between a basic discovery, like string theory, and a practical application. It may take forever in the case of string theory. But here are some examples. Between the discovery of the giant magnetoresistive effect to gigabyte hard drives took only 3 years. From the CCD discovery to digital cameras took 6 years. From the transistor to the Walkman took 7 years. From matter waves to the electron microscope took 10 years. From radio waves to wireless took 11 years. From fission to the first nuclear commercial power reactor took 19 years. From general relativity to GPS took 78 years. And from photovoltaics to solar panels took 115 years. And of course, you can explain these delays in various ways. Necessity, we didn't need solar panels until we discovered that carbon dioxide is a bit of a problem. It was the war that led to the development of nuclear power, and it was missing technology. You couldn't develop GPS until you had satellites and other things like that. So there are different reasons for the different delays. Chance is an important ingredient. I mentioned that so many of the great discoveries that have made our world what it is took place completely by accident. These are just a couple of examples. In 1856, this 18-year-old English chemist had a German mentor, von Hofmann, who told him to synthesize quinine from coal tar, and he tried to do it, but it didn't work, and instead it made a kind of smelly mess with a slight purple tint. And from that slight purple tint, he extracted the first aniline dye, which got to be known as mauve. And mauve was worn by the Queen of England and by the Empress of France in the Second Empire, and became very famous. And Henry Perkin became very wealthy. And his advisor, von Hofmann, went back to Germany and discovered a bunch of other aniline dyes and began the great German dye industry. 1896, Henri Becquerel, the son of the man who discovered photoelectrics, set out to prove that luminous minerals, his family was very interested in cold light, in luminous stuff, like it's on the watches today. Watches can't be radioactive anymore since the 1920s. Anyway, he thought that luminous bodies produce X-rays. X-rays had just been discovered, and it was plausible that luminous chemicals also emit X-rays. Well, it happened because of an incident of triple serendipity that he discovered instead radioactivity. He discovered that what he was doing was taking a luminous material and putting it next to a photographic plate wrapped in black paper and exposing it to the sun so that the luminous material would produce its characteristic radiation, including X-rays. And needless to say, the experiment worked and the film was developed. But he tried to repeat the experiment in Paris just before Christmas. And of course, the sun doesn't come out. It's not like Santa Barbara. The sun doesn't come out very often in Paris in December. And so he put this thing, prepared experiment, in a dark drawer and waited for the sun to come out. The sun never came out, so he developed the thing, and it was exposed. And he realized that, oh my God, he was completely wrong. He had discovered something unique, wonderful, radioactivity. In 1965, there was a guy working on an anti-ulcer medication, and he stumbled upon an artificial sweetener, which we know as aspartame. It's interesting, there are, of course, 5 different artificial sweeteners commonly used today, at least 5. For example, cyclamates and what is the usual one? What do you put in your coffee? What? Oh, sucralose is that's a crazy. That was discovered by accident too, no, the usual one is what do you put in the oldest one? Yeah, what? Saccharin. Saccharin. Yeah, thank you. Saccharin, of course, you know, causes cancer in Canada. So saccharin is today illegal in Canada because so Sweet and Low, which is sold in Canada, there contains cyclamates, which are legal in Canada. However, cyclamates are illegal in America because they're well known to cause cancer. So you got the picture. But all of those things were discovered accidentally. The last one I'll mention is in 1996. Chemists at Pfizer held clinical trials for a new drug to treat angina. Angina, however, it's called hypertension. And the trials failed. The drug was useless for that purpose. But half of the patients developed a very strange side effect. Happened that they were the men. And that was the discovery of Viagra. Quite accidental. Yeah, there are some accidental drugs. Here's some drugs that were discovered completely by accident. Librium for the anxious, phenacetin for the arthritic, Naftin for athlete's foot, Rogaine for the bald, Niacid for consumptives. So you can read it yourself. Revia for the drunk, sucralose for the fat, another one of the chlorinated sugars, LSD for the foolish, Haldol for hysterics, prednisone for the inflamed. There's Viagra again. Thalidomide was a disaster when it first came out, but it turns out to be rather useful for many other purposes, including leprosy. Lomotil for the loose, lithium for the manic, thorazine for psychotics, Quaaludes for the sleepless, Retin A for wrinkles, And Shentex, well, it goes on. I could list 100 more. Incredible. What about things you do at home? These are not fundamental discoveries, needless to say, but they're accidental nonetheless. Post-it notes, super glue, polycarbonate. Very important, my glasses. I have 12 diopter correction in my glasses, but glasses don't look very thick because they're made of this wonderful material. Polyethylene, Teflon, Velcro, Vaseline, microwave ovens, silly putty, Play-Doh, Slinkies, lots of toys in here. The rubber erasers, the discovery of, you don't know it, but back in the old days before rubber was imported from the New World, the only way to erase pencil marks was with bread. And bread was the material that was used as an eraser until some guy used this newly imported rubber and he discovered that, oh my God, and he made a fortune by selling erasers, rubber erasers. Corningware, that guy just died who invented Corningware. Scotchgard, Kevlar, Saran wrap, nylon, rayon, Super Bowl, celluloid, cellophane, sandwiches, potato chips, popsicles, ice cream cones, cornflakes, accidental discoveries, everyone. Incredible. Science is, as very important to notice, an extremely international discipline. It has always been an extremely international discipline. And those of us who have taught, elementary physics to people, tell them about the great discoveries of classical mechanics, always habitually focus on Copernicus, a Pole, Tycho Brahe, a Dane, Kepler, a German, Galileo, an Italian, and Newton, an Englishman. And those are the key points that we usually introduce in a physics for poets type course. All of them white, Christian, European, dead men. But today, of course, things are different, and people can contribute independent of nationality, creed, race, or sex. And I give a couple of examples. CERN has scientists from over 100 countries. The Daya Bay neutrino experiment involves a collaboration between China, America, Russia, and Taiwan. ITER involves the European Union plus 6 nations. The International Linear Collider project, which may or may not go anywhere, involves 19 nations. The International Space Station, 15 nations. Alpha. The AMS experiment involves 16 nations. And just for completion, here are the states with contacts with CERN, 113 countries. The red ones are member states. Israel just became a member state quite recently. And this involves lots and lots of countries, surprising. Not very many Central African countries, but only about 5 African countries, but a hell of a lot of countries. In talking about spin-off, I made a remark at the beginning that you can start off doing useless physics and evolve into someone who does something very useful. And there are many such examples. I just give a scattering of examples. We have Alan Cormack, who used to be the chairman of the Tufts physics department, and he was a nuclear physicist mostly. He, in his spare time, actually, invented the CAT scanner, and that led to a shared Nobel Prize for his contributions to this device, Nobel Prize in Medicine. Wally Gilbert, who was a student of Salam and a very promising theoretical physicist at Harvard, a lousy teacher, I have to say. I took his course, but he switched to molecular biology. He would do lots of useful things in wonderful discoveries in biochemistry, shared the Nobel Prize in chemistry, and he was one of the founders of and the first CEO of the Biogen company. And Biogen is now employs my son. He does public relations for Biogen. But he left Biogen while he did, and he is now a rather celebrated art photographer He has studios in Somerville and also, I think, in California. His photographs are magnificent. He uses Photoshop to the nth degree, producing some wonderful things, some of which I've bought. He's also a philanthropist, and there's the Wally Gilbert building someplace in Harvard that I guess he contributed to. Paul Ginsparg, when I was at Harvard, Paul Ginsparg was an assistant professor, and we voted on tenure. I was the only person who said yes, so he didn't get tenure, but he went off, and he was the founder of the free online archive for physics and for many other sciences as well. He would get a MacArthur Prize for creating the archive, for changing, in the citation, for changing how physics gets done, which he really did. It was a remarkable achievement in a field far removed from the days when he wrote Desperately Seeking Superstrings with me, where we compared, well, we were not nice to superstring theory. Leon Lederman, a great experimental physicist, discovery of the Oops Leon, which was a false discovery, and the real Upsilon, as well as, together with Steinberger, the discovery of two neutrinos. And he has been very active in science, technology, education, and he has created, among other things, the Illinois Math and Science Academy for teaching teachers how to teach math and science. Andrei Sakharov, my God, famous theoretical physicist who gave us a big hint about why there is a matter-antimatter asymmetry in the universe, a hint we're still trying to exploit fully. But he also was responsible in large measure for the Soviets signing the Nuclear Test Ban Treaty, and was a champion of human rights in Russia. He wasn't treated very well by the Soviets. Finally, toward the end of his life, he was released, and he was, of course, a Nobel laureate in peace. So these are just a few examples, and there are many, many, many others of physicists. In fact, one of my best students has spun himself off, too. I'll come to that in a moment. There he is. When I give this talk in China, I always talk about Andy Chichi Yao, because he was my graduate student at Harvard. He came to Europe with me when I was on sabbatical. He wrote his thesis in 1972. He decided he didn't like physics, or he didn't like me, or something, so he switched to computer science. He got a second PhD just 3 years later from Princeton in computer science, and he went off and became a major contributor, I think, to computer sciences. He's won the Turing Medal at one point. He's gone back to China. He's now has many positions in China and in Hong Kong as well. So that's another spin-off. Now, I've been talking mostly about basic science and how basic science can and does often lead to some development, some useful development. But it goes the other way, too, and it has on many occasions gone the other way. So these are just a few examples, some of which are rather familiar. The steam engine was invented and improved by Watt long before it was understood. But trying to understand how steam engines work and how to make them work better really did lead to the science of thermodynamics. 19th century inventions, three inventions that were tremendously important. By Ruhmkorff was a German engineer, untrained engineer who developed the spark coil. In fact, if you've ever seen the spark coil to the Model T Ford, it was exactly the device that Ruhmkorff had invented in the 19th century. Doug Ayer's discovery of photography and Geissler's discovery of mercury air pumps, which enabled him to seal electrodes within tubes, producing Geissler tubes, that all three were necessary for the discovery of X-rays, which used a Geissler tube, a vacuum pump, a Ruhmkorff coil, all that stuff. and photography, because the first thing that was done was Rankin produced an X-ray picture of his wife's hand with the wedding band on it, and women went crazy because they realized that men could look at them with X-rays and see through their clothing. Quite a scandal. But of course, quite quickly it became a very practical device, the use of X-rays. But also all these other X-rays, radioactivity, the electron, atomic number, cathode ray tubes, all of these very important and very fundamental developments came about thanks to the work by three characters, none of whom ever went to college. The antenna, of course, used by Penzias and Wilson to discover the microwave background was built by AT&T for early satellite communication, and it had been abandoned more or less for AT&T's purposes. It was used by Penzias and Wilson to track down some strange signal they were getting. At first, they thought it was caused by pigeons that roosted in their antenna. They cleaned out the antenna. They still got this crazy signal. They thought it was New York City, but it was not correlated to what was going on in New York City. Indeed, they were amazed to realize that they had discovered the cosmic background radiation. Gamma ray bursts were first detected by the US Air Force satellites looking for illicit Soviet nuclear tests. There was no indication of any violation of the test ban treaty, atmospheric test ban treaty, but there were some signals not coming from the Soviet Union, but coming from space, and they were gamma ray bursts, and they got declassified at some point and became a very exciting development in astrophysics. Superconductors enable otherwise important calculations. I mentioned here the four-color theorem in pure mathematics. Supercomputers are also used by amateur mathematicians everywhere to discover the next perfect number, because perfect numbers are correlated with Mersenne primes, and there are 41 known Mersenne primes. They get discovered by various amateurs or professionals at the rate of once every year or once every 2 years. We're up to 41 of them. Also, you will remember that the prime pair theorem is almost proven. The conjecture that there are an infinite number of prime pairs like 15 and 17 and 19, which differ by 2. And it's not quite proven yet, but within a decade or so, it will be completely proven, probably, almost certainly, thanks to the use of supercomputers. And that is all I have to say, except for the most important part, which is I hope there's time for you to tear me apart with questions.
I encourage people to ask questions, especially the students and so on, and ask them all kinds of questions about this life in physics. Yeah. Phil?
Yeah, speak loudly because I'm sort of deaf.
So I was in your class many years ago at Harvard.
I don't remember your face. It's all that facial hair.
At us, if you remember.
Well, if you were sleeping.
Yeah, and I wasn't sleeping. You throw hair. They were fun to watch. I had Coleman as well, so I had the.
Were we both smoking during while we taught?
Yeah, you were both quite interesting characters.
Yeah, but that's not a question.
No, it's not a question. It's just an introduction. There have been a number of interesting statements by mostly experimentalists that if they had to apply for funding to do what they ultimately did, the famous statement by Charlie Towns, for example, they never would have been funded to do it. And to what extent do you think that the way in which science is done in the United States in particular, the writing of proposals, which occupies a large portion of scientists' time these days, is counterproductive to science?
Well, my experiences have been fairly, even way back when I was starting off and, had no Nobel Prize, were innocuous in that respect. When I was at Berkeley, I taught at Berkeley for 3.5 years, I had a small Navy contract with a mathematician, Nick Burgoyne, and I think it was $30,000, which is, back in 1960 was equivalent of like $100,000. And I remember the Navy came by, and the ONR people came by and said, "Hey, Mr. Glashow, would you like another zero added to your contract?" It was like that, and I said, "No. I mean, I don't. That's enough money. I said, trouble enough spending what you give me." So things were kind of different back then. When I was, for many years, I was 35 years at Harvard, and most of that time we were funded by a single contract. The theorists, I think of I'm not describing the experimenters now, I'm just the theorists, had a contract with the Air Force Office of whatever, and proposals were written by Roy Glauber, and I never saw anything. He did all the work in writing the proposals. He's a kind of lazy guy, and he didn't spend all that much time writing proposals either, and it was kind of routine. So it's gotten harder now. In fact, I was cut out by the NSF, and I was cut down to a half month of summer salary in the summer by the. So of course I don't do anything anymore, so they don't pay me. But that's fair enough. I don't do as much as I should. But no, I've never been bothered by that, and my experimental colleagues have never complained in that direction. That hasn't, for some reason, hasn't been a problem. I mean, there are problems enough. There's not enough money, for sure. And the particle physics establishment is falling apart in this country since we don't have accelerators, and all we can do is work at CERN, but at CERN we have no authentic control, and we're just guests at CERN. So that's a little embarrassing, but that's the way it is now.
Other questions? Maybe I could ask one. You talked about your interaction with Niels Bohr, and you said he was practically incomprehensible.
Niels Bohr, I could never tell whether he was speaking English or Danish. But I didn't speak Danish, so he had his hand in front of his mouth. He had his pipe. I mean, it was very difficult to understand him, but it was a lot of fun. And I remember one incident. There were a lot of postdocs around at the Niels Bohr Institute, maybe 30 of them from different countries, all kinds of countries, including Japan and China and Russia, as well as all the European countries. And there was one time where a Dutchman showed up, and a lot of the small words in Dutch are the same as the small words in Danish. And so he said to Niels Bohr that he had made his way from Denmark from Holland to Denmark by bicycle, and the words he used, "Jeg har fisser mon vej," well, it meant go by bicycle in Holland, but it had a very obscene meaning in Danish, and Niels Bohr said, "That is very interesting." So they were one of my colleagues, Nick Burgoyne, also raced automobiles at the Roskilde track, and he had a flat tire, and this physicist newspapers were filled with an article about a Canadian physicist who won the race with a flat feeling. It was just a pun in Danish, and it was all over the newspapers, and Niels Bohr was not happy about his boys going out there and racing cars, especially racing cars with flat tires. But winning made it okay.
We have a question back there, and then a question now.
So I'll say that. So your presentation, it seems like you painted a picture. Can you hear all right? I'll shout louder. Shout louder. So the presentation seems like that these scientific discoveries have been a mixture of, like, on one hand, we have no idea if they are going to be useful at all. And and on the other hand, a lot of them were by accident. And so in this world of like the modern era of limited funding and limited time, is there any way that we can choose which things we might want to focus on to try to like lead us to figure out what could be useful in the future?
How do you make your decisions? I don't know. In particle physics, maybe you wait until there's a big hungry country out there that has lots of money that wants to build a 100 TeV accelerator, like, for example, China. And they want to win a dozen Nobel Prizes with all of the physics that would be done. They want to develop a technological infrastructure that can make possible their development of this machine. I don't think they're dedicated simply to doing physics and winning Nobel Prizes. I think they want to develop industrial capability, which they do not currently have, and they can do that through large projects. That is also the attitude at CERN. CERN also has the dream, a less realistic dream, of building a large accelerator, again, with the not entirely for the sake of learning about the universe we are born to, but hoping to develop industrial capability beyond what they presently have. And they make arguments, I don't know how realistic they are, that the monies that CERN gives to industry to commission various new magnets or other parts of the detectors and things, that money gets amplified by a factor of 6 or something like that in terms of the future capability of these companies. Now, whether this is real economics or not, I do not know, but there arguments like that have been made about economic spin-off from developing new technologies.
Question up here. Yeah, you go ahead, raise your hand.
How responsible are scientists for this public perception that we're not useful?
I don't think there is such a public perception, actually. I think I find in giving various talks and in teaching an energy course at BU, I find that there's an attitude, a feeling that the technological problems associated with global warming and eventual shortages of fossil fuels, just complementary problems, they'll be solved by new technologies, that the scientists can do anything. There's very much that yes, of course, there's a lot of people who distrust science in all of its forms. There are the people who deny global warming. There are the people who refuse to give their children measles shots. There's a lot of that in this country, a lot more than there is in, say, France and Germany. But there's also a lot of hope among more normal people, but it's an unreasonable hope that we'll come up with some battery that's 5 times better than the current batteries, so we can make cars affordable cars, electric cars that can drive more than 40 miles on a charge. The Tesla, of course, I've seen a bunch of Teslas since coming to this town. This is Tesla town, but that's a very expensive car. I think it's $100,000 or so if you want 85 kilowatt hours of electricity stored there, which is enough.
Normal people, but the investment in science from the government has gone down.
It has gone down precipitously. It's sort of not gone up with inflation over many, many years.
We actually own some of that burden.
You think it's our fault?
At some level. I can't say it's 100% our fault, but at some level, we ask these questions appropriately, but at the same time, we don't seem to figure out why is it that they don't throw money at us.
I haven't solved that problem. It's really a problem, and it's a problem in Europe as well. There's a catastrophic reduction, especially with economic situation in Europe as it is today. The salaries at universities are precipitously reduced in countries like Italy and Spain, and research funding is hard to come by. It's very bad.
Ed Shapiro wants to ask a question.
Ed.
If you came across a little note some probably 2 or 3 months ago from they found some evidence that some, say, 2,500 years ago, there was what we call something warming here. I don't remember what the whole title is, which is an indication that what we call warming effect is a fake.
Sorry, I don't quite get what you're saying. Some people in Colorado said that something happened 2,500 years ago.
I think a global warming.
There was a warming period. Okay. That may be true. I don't know.
Some danger of the result of our actions is a fake. It's not real. It's just a process. Very natural.
There are people who deny the connection between carbon dioxide emissions and global warming.
Absolutely. Yes.
Of course, there are such people. My brother-in-law, a brilliant mathematician, is one of them, but I'm not.
Okay. Other questions? We have no further questions. Oh, okay. A couple questions in front and then maybe.
Oh yeah, the question, more the better.
So, Dr. Glashow, I'm an undergraduate here at UCSB.
Good.
And
Good place to be, yes?
yes.
If you were at BU, the school would be closed.
No, yeah. I'm really inspired by your work, and I was wondering what decisions or what fields you chose to follow, some choices early in your career. What do you think contributed to your success?
Yeah, that's a question. Look, a part of it, I think, first of all, I went to the Bronx High School of Science, and the Bronx High School of Science has 8 Nobel laureates. No other school in the world has more than 4. So that's remarkable. But you might think that the science courses were good, but they were really lousy. I mean, there was a lousy biology course, a lousy chemistry course, a lousy physics course. I took the advanced physics. I didn't take the advanced physics course because it consisted of taking apart an airplane engine and putting it back together again. It was really, what was important was the colleagues. I had the peers, not colleagues, they're high school kids. So among them was, in my class, was Steve Weinberg. We were very good friends. Gary Feinberg, who was also became a professor at Columbia. Another fellow who's Morton Sternheim, who's a professor at UMass. And we kind of hung out together and pretended to learn. Like one day I would say to Steve, hey, last night I learned all about the calculus of variations and you can do all these things. And he said, really? And so the next day he comes back and he says, I learned quantum mechanics. But of course that wasn't strictly true, but we were. One example, I went to in New York City, all kinds of things were happening, and around 1948 or so, I was in high school, Yukawa won the Nobel Prize for suggesting mesons, and there was a public talk that I went to. It was open to the public, so there was Yukawa. I didn't understand. His English was not very good, but even if it were perfect, I couldn't understand. I was a high school student, didn't understand anything. At the end of the talk, a bunch of people in the front row, who were no doubt famous physicists of the time, were screaming at Yukawa, and there were the words, I remembered the words, it's a scalar, it's a vector, no, it's a pseudoscalar. What the hell are they talking about? And I had no idea. So I was fascinated by that sort of stuff. And being a Jewish immigrant family from New York, I mean, I'm first generation American, there was a fascination with Einstein, and so he was held up as a great hero. So I somehow, and chemistry sets were interesting. You could really make things explode with chemistry sets. Today you can mix all the chemicals together and make an omelet and serve it to your sister, and she won't even get a stomach ache. I mean, but back then we had some interesting chemicals. And so okay, you get the picture.
Yeah, he mentions Bronx High School and Weinberg and so on.
But I didn't talk about making little bombs in Inwood Hill Park.
And you had somebody else said. Okay, other questions? Yeah, in the back.
As a professor or a student, how often, if at all, have you felt defeated by maybe a doubting of your intentions or overwhelmed by the amount of work in your future when that and
How often
like that?
was I overwhelmed?
Overwhelmed or defeated by your intention, something?
And if so, how do you motivate yourself to get beyond that and keep going?
Yeah, how do you
As
keep
scientists.
going as scientists if you're defeated?
I'm beginning to wonder about that at my age, because I may be running out of ideas. But back when I was a kid, there was always, I like to put it this way, back in the 60s and 70s and 80s, when I did most of the things that I did, there was a lot of low-hanging fruit. And so we just had to reach up and pick the peaches and the grapes off the trees. Here's an example. BJ and I invented the idea of this charmed cork. We gave it its name in 1964. And it doesn't take much to realize that with this fourth quark, you can jiggle the structure of the weak interactions and suppress these strangeness changing neutral currents that were there even in a theory without not unified theory. Anybody could have done this work. And today, anybody would have done it. There would be 10 papers. But from 1964 to 1970, nobody had the idea that the fourth quark could actually serve the purpose that is implicit in its name, charm. Charm is a device to avert evil, and the evil that charm averts is strangeness changing neutral currents. But why did it take 6 years for that fruit to be waiting for Iliopoulos Mayani and myself to pull it off the tree? Different times.
I guess it's just fortunate circumstances for you. I feel like people this day, today have the same opportunities here and there.
I think theoretical physics has gotten too difficult for me today. I don't understand the stuff that David does very well at all. I appreciate it as brilliant, but I don't understand it.
We have a question here.
Yeah, so similar talk like this, would you try to get to the congressman?
My experience talking to congressmen has been not entirely satisfying, but I have tried to. The only person who was really responsive was Ted Kennedy when he was alive and well, but that was a long time ago. I mean, Ted, for various reasons, he even came to our house and got drunk.
So maybe on that note.